So, yeah, as Jerome said, I did this talk at Austin where I talked about how containers are built up. And one of the things I heard myself saying was, we're using Syscalls to exactly what does that mean? So what are these Syscalls that I'm talking about? I really want to dig another level down. So in this talk, I'm going to be explaining what Syscalls are and how we use them. I work for Aqua Security, and we have products that help enterprises secure their containerized deployments. So I'm pretty interested in security these days, and I want to talk a bit about how Syscalls relate to that and other runtime profiles. And then we'll end up with a demo of an exploit to kind of show some of these concepts. So let's start by considering what is a Syscall. When I first went to explore this, my first port of call, like any good citizen of the internet, I went to Wikipedia. And Wikipedia gives us a pretty good starting point. It tells us that Syscalls are the way that programs, your user space code, request services from the kernel. So it turns out there's a whole load of things that code in user space can't actually do for itself, and it has to get the kernel to do it because it has to be done in privileged mode. And the kind of things we're talking about are really fundamental things, like every time you want to write to a file or a device, every time you want to make any kind of communications call, you want to create processes, you want to find out what time it is. And of course, we're interested in containers, and if you want to create a namespace, you're going to use Syscalls to do that. So they're really fundamental to what we do. Now, one of these things on this slide is kind of a lie. So if you know what it is, you can tell me later if you kind of guess what it is, because I will come back to it. But bear in mind, one of these things is not quite true. Okay, so broadly, I'm talking about what Syscalls are, but let's see some of them in action. I'm sure a lot of you are familiar with a utility called STrace. And STrace will show us exactly what Syscalls are happening. So if we do something really simple like hello DockerCon, lots of Syscalls happen. Now, I could step through all of these system calls, and it would be a really dull talk. So I don't propose to do that. But what I do want to highlight is a couple of these. So the first one that I want to point out is execve. Is this big enough? Shout if you're at the back and it's not big enough. Big enough, okay. So execve is the system call that runs a program. In this case, it's running echo. Lots of stuff happens that we'll skip over, and eventually we get down here to the write system call, where we write 16 characters to file descriptor 1, which I'm sure you're all aware is stood out, and that's where the actual work happens when we made that echo call. So whenever you do anything, even as simple as writing to the screen, even if you're not aware of it, you are invoking system calls. And you probably, occasionally, you might call a system call directly, but usually you call a library function, which calls another library function, which calls another library function, which calls one of these kind of system call libraries. They tend to be language specific. If you're using C or several other languages, it will boil down to a library called libc, which implements these syscall functions. There are a few flavors of this. For example, glibc, which is the GNU version of libc, and it has all the syscall functions defined in it. Any Go programmers in the room? Yeah, quite a few of us. Excellent. So as Go programmers, we have a Go native syscall package that implements syscalls for us. And I've got an example here of the write function, which just looks like a normal write function. This is within the Syscall package. If we look at what's happening inside that function in the Go package, we can see it calls a function called Syscall. And it passes in as the first parameter which Syscall it is that it wants to invoke in this case, it's syswrite. And there are some 330 odd different system calls, all given their own identifier like this. Some of them are super weird and esoteric. Some of them are really kind of obvious, read, write, open, close. I imagine everybody in this room can guess what those do relate to a file. Occasionally, this list grows. Fairly recently, for example, the setNS Syscall was added, and that was needed so that we could enter namespaces, so we could put a process into a namespace. Without that, we wouldn't be able to do things like Docker exec. Later on today, I believe, Tycho is going to be doing a talk about changes to the Linux kernel that are container related. And so things like adding new system calls would be a good example of that. So we've got this function called Syscall, and it's passing in this identifier. But then what happens? The man page tells us that Syscall saves some CPU registers before it makes the system call and restores them when it comes back from the system call, but it doesn't really tell us very much about what's actually going on. So to find out more, we can look at this table of Syscall parameters that gives us some clues. So this is saying for each of the system call codes, here are the set of parameters that we need to pass in. And the clue is really in that header at the top of the table, where it's basically describing which register. This happens to be for an x86 processor. It's saying which register those parameters need to get put into. And we can look at the assembler code of what's actually happening inside that syscall function to see even more. Now, I don't use assembler all that much, but fortunately, this little extract from the GNU C library was pretty easy to read, and the comments make it pretty clear. So the syscall code, that identifier, goes into the AX register. If we have other parameters, they go into the other registers as defined in that table we were just looking at. And then we call this thing called Syscall. And at this point, we're looking at a machine code instruction called Syscall. So what's that doing? So that is the point where we transition into the kernel. So it used to be that chips would actually do a normal software interrupt, and I think it's a perfectly good sort of mental model to think, okay, my user space code sets up those registers, and then it does a trap and says, basically, kernel, I need you to take over from here. The kernel, in privileged mode, can look at that code in the AX register. It's got a lookup table that points it to some machine code instructions somewhere in the kernel code that tell it how to execute the thing that that syscall needs to do. So, for example, writing from a string of bytes into a file descriptor. And it does that work, and then it can basically return control back to user space land. This approach of setting up the registers with those parameters works for any different kind of chipset. So you have a table like this that tells you for a given chip which parameters go into which register, because the different chips will have different names for their registers. So if you want to port Linux to a different piece of hardware, a different chip, you need to just implement this syscall interface, and that's all you need to do to run your Linux application code on that chipset. Might not even be hardware that we're porting to. So for example, when Microsoft implemented Bash on Windows, what they've actually done is they've implemented an emulation of that syscall layer. So you don't even have to implement all 300-odd syscalls, because it's just one function. You just have to implement the set of syscalls that your Linux code is actually going to call, and then you can port it to run on whatever platform you want it to run on. So syscalls are kind of giving us a portability layer as well. Now, this is where I confess to my lie earlier. that transition from user space to kernel is a little bit expensive, and you could end up doing it a lot, thousands of times a second, very, very typically. So to optimize for some of the really common syscalls, some architectures actually support user space implementations of Syscall in a thing called a virtual dynamic shared object. So this VDSO library gets loaded into your user space program, and it gives you a user space implementation of a few system calls. They typically are things like getting the time or CPU-related function. And it's things where that particular chip can safely give you time information or CPU information without the transition to the kernel. Now, the thing about this is, if you're using STrace to see which system calls are being called, it's sitting at that transition between kernel and user space. So if you don't do the transition, STrace doesn't see those calls happening. And we can take a look at that. So say, for example, we do something like time how long it takes to sleep for a second. And kind of obviously, it's slightly longer than 1 second. Now, if I strace that, oops, and I want to follow into any child processes, and I want to sum up the count of each different type of syscall, and then I just run that again. And it takes literally a second to tell us which system calls it used. And we can see down here there's a nano sleep. That sounds like it was the sleep thing happening. But there's nothing else in here that looks related to timing. And yet we know that timing happened because we could see that information about it taking 1.00 whatever seconds. So let's look at the dynamic objects in that time function. And we can see here there is, where's my mouse gone? A VDSO object linked in. If I find, we couldn't see which file it was actually referring to, but if I look for all the potential options that match VDSO, and I look at information about my system, so I can see my kernel build, and I can see that I'm on a 64-bit platform. So I'm fairly confident that, oops, this one here is the VDSO object that will have been dynamically loaded. And just to kind of validate what I said about time and CPU functions, we can see that the names of things inside that object all relate to things like get CPU and get time of day. Those are the user space implementations of those syscalls that work on this particular chipset, and that's why we didn't see those time functions in the strace output. So if you, when I said I lied, if you identified time and date, you get a clap on the back. Okay. Oh, VDSO, I think Tycho is going to be mentioning some VDSO-related, features in his talk later as well. So thinking about what we can do related to security with syscalls. You may well be aware that there's a thing called seccomp, which stands for Secure Computing, and it's a way of limiting the system calls that a particular process is allowed to call. And you might have a profile that looks kind of like this in JSON, and it tells you which system calls you can call, which system calls you're not allowed to call, and maybe some exceptions. There's a default seccomp profile that gets attached to containers, well, by default in Docker, unless you specify another profile. And that default profile includes a lot of very sensible things, like, for example, you're not allowed to call the reboot system call unless you specifically pass in the capability flag sysboot saying, no, I really want to be able to do that. So I wanted to test this out. So I wrote a very, very simple bit of code, little Go program here, that all it really does is call the reboot syscall and tells us how it got on. So I think, yeah. So if I run that code inside a container, it picks up the default Docker profile, the default seccomp profile, and we can see it's not allowed to call the reboot system call. So what happens if I then pass in that capability flag? Well, this time I didn't get an error, so presumably I did actually call that reboot function. Now, when I first did this, I kind of expected that would actually kill my machine, and this would be very dramatic. It turns out that from kernel 3.4, thereabouts, the reboot syscall became namespace aware. So essentially, it knows this process is not running as process ID. Well, it's not running. It's running inside a namespace, and therefore, I will just kill the container rather than killing the whole machine. So that's kind of a nice example of a container-specific improvement to a syscall. Okay. If you want to build a seccomp profile, you need to know which system calls your containerized code is going to run. And you can imagine if you ran STrace and you got the list of syscalls, you could convert that into one of those JSON format seccomp profiles. But how do you actually run STrace over that executable inside the container? Because you can't just run strace docker run, because you would be stracing the Docker command line utility, and that command line utility sends messages to the Docker daemon to actually go and create the container and run the executable code. You wouldn't be stracing any of that, because that's happening in an entirely different process. So you can't directly strace it. Maybe you could exec in. And I have a couple of processes here. Maybe you could do something like exec into, I've got a little web process here called hello, and maybe I could try and run a shell in that, and then run strace inside that. That isn't going to work if, like this example, you don't have a shell inside this container. In fact, this container image just contains my binary executable put into the scratch image. So there is no shell, let alone strace. So that's not going to work. There is an alternative. You can run strace in a separate container and attach it to the namespace of the container you want to trace. So trace this one. So I have a container called Ubuntu strace, or an image rather, called Ubuntu strace, which contains Ubuntu, has strace installed, and I can run that in the same process ID namespace as my hello container. I can see that hello executable running as process ID 1, and I can do things like strace. I'm going to follow into the threads that my Go executable has, and I can specify process ID 1, and I can do things like curl to localhost. I think this is 8080, and lots of stuff happened inside my web server, and we were able to capture those syscalls happening in the attached process. So it is possible to run strace against a container in this shared process ID method. But that might well miss stuff. If I had initialization code when I started up that web server code, that hello container, that would have been totally missed by strace. There's no way to kind of attach to that process before it's been started. Plus, even if we captured all the syscalls, we know from what we've seen about VDSO, it might not really be a complete list of the syscalls that we need in order to run that containerized code. And your seccomp profile needs to take account of any syscalls that are needed after the seccomp profile has been attached, but before your container has completely started executing. If there's anything that the container D or any part of running the creation of the container needs, that needs to be included in your seccomp profile. So can be a bit tricky, and they're not necessarily super portable. So we could step up kind of another layer of abstraction by using a Linux security module called AppArmor. Now, I mention these because they can also be associated with Docker containers, much like you can associate a seccomp profile with a Docker container. And AppArmor profiles, rather than looking at the Syscall level, look at what a program can do in terms of accessing files and which capabilities it's allowed to have, what sockets and network and mounts and all sorts of things like that. Interestingly, they're associated with a program at a particular file location rather than being associated with a process. You want to generate an AppArmor profile. It's not really trivial. Is there anybody here who is using AppArmor? A few. And do you feel, keep your hands up if you feel like you have a fully maintained and sort of complete profile that you're really happy with and that's easy to maintain? Yeah. So it's non-trivial. If you want to generate an AppArmor profile, you install these AppArmor utilities and you do things. You start by creating a blank profile with one of these utilities. You put your profile into complain mode, run your program. It generates logs as the program runs. You can then review all of those logs and decide whether they should be allowed or not in the AppArmor profile. Maybe you're going to manually edit that profile when you finish. And basically, by the time you've got to the end of this, you will have lost the will to live. You end up with something that looks a little bit like this, which is kind of on the face of it relatively, I can make sense of which capabilities that needs and what file access it needs. I am a little bit concerned about having hash includes because that screams difficult to maintain at me. Jess Frizzell did a really good tool called Bane. She called it Bane because maintaining AppArmor profiles was the bane of her existence, I believe, is the quote. It converts from a more human-readable format into the AppArmor profile. But even with that, it's not really easy to kind of keep these things up to date. If you want to generate an AppArmor profile for containerized code, you have another challenge. So you've either got to run that code on a host so that you can capture the profile and then sort of stop running that code on your host because you don't want to do that. You want to run it in a container. Alternatively, you can run AppArmor inside a container. It is possible. I tried it. Yeah, it works. These are the settings you need to make that happen. But the bottom line is getting these profiles to be correct and keeping them up to date is a really hard thing to do. The profiles are fundamentally difficult to keep up to date. But I'm not dismissing them by any stretch because they are really, or they have the potential to be really, really powerful. Particularly if you think about microservices. So imagine a microservice that basically, it has one job. So it's really easy to reason about whether or not it's doing anything that is not part of that one job. It's much easier to look at a microservice and say which executables it should be allowed to run or what network traffic it should be allowed to use. And if you can capture some kind of runtime profile that represents what that microservice should do, and if you can maintain that, that can be a really powerful tool in preventing exploits, because anything that isn't part of what it's supposed to be allowed to do can be flagged up or prevented. So I'm going to show a little bit of an example using the vulnerability called Shellshock, which comes from a few years ago. I imagine some of you will have at least, who's heard of Shellshock? Yeah, most of you. Shellshock was a vulnerability in Bash, where if Bash was evaluating environment variables, it could end up also executing arbitrary code even if you didn't really intend it to do that. So I have a container, oops, running a version of Apache with that vulnerability within it. So, right. What we're going to do, we're going to attach to that container and trace it a bit like we did before. This time I'm going to attach to Shellshock. Okay. And I can look at the running processes. I cut this down, so it's only got a couple of these HTTPD processes running, and I can STrace those. For this example, I'm only interested in that execve system call that we mentioned before. So this is the system call for running an executable. I want to follow any children that get created, and I'm only interested in a couple of these processes. Okay. So if I curl to localhost 8000 and let's find, there's a CGI script here called hello. And if I hit that, we see a web page created. CGI is kind of the prehistoric way of creating dynamic web page content. That's the best of my understanding. And we can see that when we hit that particular URL, it did execute a CGI script. So that's normal behavior. I also just want to show this location, env.html, which gives us a 404 response. So there is nothing at that location. Okay. Now, if I curl to that CGI script and I pass in a user agent header that is formed in such a way that we can exploit the bash vulnerability. And in here, we should be able to run any code we feel like. I'm going to run env, and I'm going to send the results of that into env.html. So we can see that my attack has been able to run not just the, oops, where's it gone? There we go. So we've not just executed the HDI, the hello CGI script. We've also been able to run, or we have executed a couple of other programs. You could argue that that web server has no business running, certainly no business running env. So if we could prevent env from being run, we could prevent this attack. And we can see the results of this attack by going back to that web page here. We can now see through that attack, I can make the whole environment accessible just through a web page. So it was a pretty terrible and scary vulnerability. And it was a vulnerability that could have been spotted if we were able to look at different processes and constrain which executables they were allowed to run. So you can do that kind of thing through profiles like AppArmor. As we discussed, it's not super easy to do that. And that's why tools like Aqua exist. So that's one of the things that we try to do, is to make it easy to define the set of executables that you're allowed to run in a given container or a given microservice. So if you want to find out more about that, do come and talk to me or one of my colleagues here at the show. But just to recap, we've seen how Syscalls work. We've seen how pretty much whatever user space code you're writing, you're going to be invoking these Syscalls all the time. If you want to find out more, and if you want to learn more about VDSO, do come to Tycho's talk later on today. We've seen the power of runtime profiles, and we've seen how actually they're a little bit tricky to keep up to date. And the kind of the reality of people using them in practice is they find them hard to keep up to date. But we have seen how, at least in theory, they're very powerful. Finally, as a kind of a reference for further reading, if you want to find out more about how STrace works, I thoroughly recommend Julia Evans's STrace zine that explains it in a really lovely and accessible and nice way. I've also got a reference there to a repo where I build a very, very basic version of STrace from scratch in 60 lines of code, where you can see how STrace uses the ptrace system call to intercept those system calls as they go by. So with that, I'll say thank you very much. And if you want to come and learn more, the AquaSec team, we're based at booth G10 in the expo hall. I think we have a couple of minutes for questions. Okay. Yay!
For the questions, we have 3 microphones. There is one on front here in the middle, and there are 2 microphones kind of in the middle, both left and right. Or you can also shout your question, and Liz will repeat it.
If I can hear it. We got some questions. Any questions? I can see a question there.
Can you please tell how safe is STrace? You added some container traced, some very long process, and trying to guess what happens, how safe this actually was. Is it best?
Okay, so the question is, how safe is it to run STrace on a given other process or on a given other container? So the way STrace works, I mean, actually running the STrace executable, I've not reviewed the code myself, but I'm sure the STrace executable itself is fine. Although I might come back to a little war story in a second. But in order to run STrace, you need the ptrace capability. Because STrace, as I mentioned, uses ptrace. And ptrace is super powerful. With ptrace, you can attach into another process, and not only can you see these systems calls going by, you can manipulate memory inside that running process. So you can read anything you like. So if you were able to attach to a process that perhaps had access to, I don't know, hidden data, some secret information that you shouldn't have access to, you could see it using ptrace. You could manipulate a program to, I don't know, change passwords to something of your own choice. So if a bad guy gets ptrace access to a process, they can do all sorts of interesting and potentially evil things with that. So that's why usually ptrace is turned off. I mean, I think there's a certain amount of belt and braces, because, like, how did they get in there in the first place? But yeah, it's generally wise. I would definitely say run your containers in production without the ptrace flag for safety's sake. The war story was I tried to run STrace as part of setting up some of these demos. I tried to run STrace over something quite large, and I was trying to capture all of the output, and it did manage to bring Docker entirely down, and I haven't raised an issue about that yet. But I think it can be overwhelming if you're trying to STrace too much. That's not a super good story, but I need to dig into that a little bit more, because it was kind of interesting that it could just kill the daemon somehow. Any more questions? Oh, yes, down here in the corner.
What do you think is the biggest or most common mistake people make when they run containers?
Oh, the question was, what did I think the biggest mistake that people make when they run containers? And I'm going to qualify the question to sort of be with a security mindset. Is that okay? Yeah. So the biggest stroke simplest to fix mistake that I see people do is building secrets into their container images. A surprisingly large number of people do put passwords and things into their container images. And I'm just flagging that as a really, really simple thing that you don't need to do, and yet people do that. Yeah. Any more questions? It's really hard to see, the lights are shining in my eyes. I still can't see the wave, but I believe you. To add capabilities in a Docker stack, you definitely can add capabilities flags. So when you do Docker run, you can specify with the cap add flag any additional capabilities that you want to add over the default set. Sorry, I'm struggling to hear. Hey, here we go. Microphone.
Oh, sorry. Hello. The thing is, the add capability just changes the bounding set of your process. It doesn't add capabilities. That's something people get wrong. You know, when you use capabilities, you've got the capabilities and you've got your bounding set, the border of your capabilities. And the add capabilities just changes the border, but it doesn't add capabilities. That's something people get wrong most of the time. Sorry.
Okay, so yeah, it is certainly true that there is a default set of capabilities that you don't get when you run Docker, and you can add them. Whether that default set is constrained, Jerome probably knows a lot more than I do.
Yeah, the default set is pretty restrictive. There was recently somebody pointed out, hey, if I give cap sysadmin to my container, it can do some really nasty things, and it might even be able to break out of containerization. I was like, it's kind of by design. Cap sysadmin doesn't give you full capability by, like, in theory, but at the same time, it's this kind of big bag of capabilities. Like everything that is not in other capabilities usually ends up in cap sysadmin. So when you give cap sysadmin, it is kind of, I really needed that container to do that thing anyway, so it might be able to break out. So there's this kind of acceptance that, yeah, we try to restrict capabilities in containers, but sometimes if you want to do something beyond just running an app in a container, you have to open that Pandora box and accept that the containers will be able to break out.
Yeah, I think I'm not going to pretend that I know everything there is to know about capabilities, but I do know in the man page it does talk about cap sysadmin being, overloaded, and there's certainly quite a lot of discussion about, maybe that wouldn't have been what, if you could turn back time, it maybe wouldn't have quite the same power.
Okay. No more questions?
There's one more over there.
So, yeah. Yeah.
Okay, see one over there.
Yeah.
Oh, there's one here as well.
How safe it is to run views inside the Docker container?
To run Fuse? I am not an expert. I don't know if you can answer that question.
I think since we are time is over, but feel free to come over here when you can chat about using Fuse in containers just after, because we did that in the .cloud days a while ago. Thanks a lot. Please, one more round of applause. And the next talk is going just after lunch at 2 p.m. Thank you.
Thank you.